Then welcome everyone. Today's speaker is Dr. Everett Schlawin. So Everett is the assistant research professor at University of Arizona. He received a PhD in 2015 from Cornell, if I remember correctly. And he's been very busy with the wonderful JWST data. So we'll hear from him about JWST's first stairs at transiting exoplanet systems. Everett, the floor is yours.
All right, thank you very much for having me. And sorry I can't be there in person. I just feel a little sick, and in case I have COVID, I don't want to spread it around. So yeah, I'm very excited to tell you about some of these very first stairs on transiting planet systems. And this has got contributions from the NIRCam team, Space Telescope, NASA Goddard, European Space Agency, and many more. And I apologize if I haven't cited your work properly. So I'm going to focus a lot on the instruments and performance of JWST. That's what we spent 6 months dedicating our time to during the commissioning period. And then at the end will be a little more of the early release science that came from, or the early observations. So I'm going to start with some highlights from commissioning, talk about how the time series modes were commissioned, talk about an effect called the tilt events, settling time scales for the instruments and performance, and 1/f noise, and then finish with the early release science observations of a hot Jupiter. So I'm going to start with some highlights from commissioning, things that we learned along the way, and some experiences. It was really a pleasure to be part of the journey with JWST from when it was coming together in NASA Goddard. You know, it started well before, decades before that, but I was happy to join and watch this journey across the nation, then boat to French Guiana, and then out to the second Lagrange point. And as it was away on out to L2, I had this nightmare. I woke up and thinking that I dropped one of the lenses of NIRCam, and I was so freaked out. But fortunately, it was a million miles away at that point, and there was no damage I could do like that. And so we're very excited to see this so many things go well, and then look at the very first planet systems. So the commissioning process was at Space Telescope Science Institute. Here's some pictures. We had an amazing team that I loved being part of, and it's incredibly dedicated scientists who kept the things running and 24/7 and through every challenge that was thrown at them. And so yeah, it was one of the nightmares I had. Did some damage to the telescope. Another nightmare, and it was probably not the most likely scenario, but something I worried about was that the mirror, the cover, the remove before flight cover would not be removed, or something would happen catastrophically. It would prevent light from getting into our instruments. And so it was such a joy when on February 2nd, we turned NIRCam was on. We took some exposures with real photons, and this was the first picture. NASA didn't share this one because it's a little confusing. What's going on here is there's a cluster of stars. We're looking at a large Magellanic Cloud, and there are 18 copies of every star. So they're autofocused and out of phase. So it was quite a kind of messy picture, but it made us so happy because it showed we had light across our detectors even before the instrument was fully cold. And so this was the real first light. And then the next process was trying to figure out for those 18 copies, from the 18 mirrors of a bright star, where were they in the sky? And they mapped out this huge area in order to find all 18 copies of the star from the different segments. And then amazingly, the mirrors were just so well aligned to start with. It was just in a small fraction when they occurred. So they were able to, this Wavefront team has been really fantastic, working with us on NIRCam the whole way through the mission to try to get the best performance we can out of the telescope. And so they were able to identify these mirror segments and begin the process of aligning and phasing the mirrors. So this is the very beginning of the process, and I'm going to skip all the way to the end. The most in focus image. This is actually the best most in focus image we'll ever have for the lifetime of the mission, because it was set up early when we were just trying to optimize for near cam, and then we had to optimize for the other 4 instruments. So it's just a tiny bit different from this early best focus. And so it's just incredible. It was the main point was looking at this bright star and examining the PSF, but then in the background, I'm a planet person, but in the background, just seeing all those amazing galaxies was just truly phenomenal. One of the things we were worried about, we had a team member, Randy Kimball, especially was checking for this, was any ice that could condense. So, launched French Guiana is a really humid place, and we launched with potential water and carbon dioxide that could condense on optics. And so Randy Kimball, we called him Iceman because he kept checking every day. Did you look at the images from near cam? Did you find any ice? Did you find any ice? Because we were looking for this little dip that could happen. And there were a few mitigations we could make if there were any ice, if there was any ice on the optics. And the beautiful thing is that the spectrum just didn't show any ice. And so we didn't have to worry at all about that on our detectors and optics, or MIRI would be an instrument really where all that ice would go. And so it was just wonderful to see no ice. And actually, when you compare the orange line here, the exposure time calculator had kind of ice built into our expected performance, partly because the lamp we used on the ground had ice on it during the initial test. And so it was just wonderful to see nothing like that and this beautiful throughputs from the telescope. So we had this Iceman who was just always worrying about ice, and Jaron, I would say he was like Maverick, showing it. Indeed, the spectra looked really good, and we didn't have to worry. So one of the many great joys that we had when pointing JWST at our first targets is that everything was working better than our predictions from the ground. So again, these orange lines are the exposure time calculator predictions, and then the blue lines are what was measured and counted. So this is a near cam instrument. We could see this across the instruments that they were performing, getting higher throughputs, because we didn't know all the throughputs and exact properties of the grism from the ground. And so one of the first things that we could see is not only we were getting really sharp images, and that the throughputs are better than the predictions from pre-flight ground predictions. And then interweaving with these commissioning, they were doing these secret early release observations. We knew so much about the observatory and our instrument, and we were getting to see all these engineering details but these were highly secret images that we had no idea what they looked like, but sometimes we could figure out based on where the telescope was. If you happened to be pointing when they were taking them, if you were sitting on the console, you could realize what the object was, but that was about it. And so we were just as amazed as everyone in July 12th when they came out with these beautiful images. So those are just some highlights I just wanted to share from our experience commissioning. Now I'm going to move on about what we learned about the time series modes from the commissioning period. And so we had to kind of make a decision on what target to look for to verify how well the time series modes. We wanted to make sure they were working correctly, and that also we could calibrate, we could understand what would happen if there was a change in brightness. And so kind of the first thing, we could verify that they're working well just by looking at any star and just finding a quiescent star and seeing if it's stable. But the real key is when we're measuring transiting systems is to see how much the light changes. And so that's why we ended up converging on an exoplanet, but there were rules against in commissioning doing science. So we had to find an exoplanet that was kind of boring and flat, wouldn't have a lot of features in its spectrum, so we wouldn't be sneaking in science and we'd actually be using to verify. So we were able to converge on an exoplanet HAT-B14, which has a high surface gravity, not any expected strong features that we could use to verify the transits. And so we looked at it with three different of the three near infrared instruments, near spec, nearest, and near cam, to see if we could recover this transit and what kind of precisions we could get on it. And just right off the bat, the light curves were just really fantastic. Usually when you look at transits are small changes. Here is like one that's less than 1%, and there are going to be many smaller planets too. And usually these light curves are just dominated by systematics. But right off the bat, you could just see this incredibly precise transit without a lot of data analysis needed to remove systematics. And then the mirror instrument, they chose a brighter target, so they ended up choosing a more challenging one. So when you just look at this light curve, it looks messier, but actually it's looking at a transit that's 10 times smaller. So actually the performance for MIRI right off the bat was also really excellent, with the little acetylene timescale at the beginning. So I'm going to focus a little more on the near cam, since I'm part of the near cam team, a little near cam centric. We'll talk about the HAT P14 observations we made. The near cam instrument, the near cam has dichroic, so it gets short wavelength observations and long wavelength observations at the same time. So on the short wavelength, we used this weak lens, which defocuses the light. That's why you get this hexagonal shape for the star you're looking at. And then on the long wavelength, we have this grism. So you get these two, the short and long wavelength images and time series simultaneously. And one thing that was just beautiful right off the bat is how well JWST's pointing works. So this is 1.9 milliarcseconds. That's just showing you the scale, or in terms of pixels, it's far less than 0.03 pixels of motion when JWST is staring at a target and running the fine guidance sensor. So this is just incredibly good, because a lot of systematics that happen with time series are when the telescope is moving, and we see this, the ground is especially awful in this respect, and so you have to do all sorts of corrections for motions. But looking at the detector, we did this pretty deep analysis of the cross hatching that can happen, this structures that happen within a pixel of the detector. And based on what we saw, this kind of pointing, we thought it would be a factor of a few larger than what we saw. It would be 6 parts per million. If it was down at this 0.3 milliarcsecond jitter that we see, it's only 1 part per million change in flux expected with this kind of jitter. So this tells us that the pointing is really not going to be a big concern for systematics on light curves, and this just bodes really well for the precision that we can expect in the future. And so we also found that the noise performance is really good. So on the theoretical limit of what you could expect for this short wavelength time series on the left was 107 parts per million scatter. On short time scales, it's 130 parts per million, just fairly close to this theoretical limit, and just far below anything we've seen before in other telescopes and observatories. And the right is what I call a dynamic spectrum. So each row in this image is the brightness as a function of time for given wavelength. And so we found you don't see a lot of structure in the vertical direction, because we chose a planet that's has very little atmospheric features in it. And so we found on these high spectrum resolution observations are also getting close to this theoretical limit. So those are that's what we were looking at in the time series commissioning. Now I'm going to talk about some of the effects we learned about to be aware of for the future. And one of these is called the mirror tilt events. So you look at the transit light curve we had for the long wavelength, you can see that right in the middle where the transit happened, there was this jump. It really had us scratching our heads for a while, trying to figure out what was going on there. And we also looked at both we had the short wavelength and the long wavelength with near cam, and then also the fine guidance sensor instrument. And that also saw a jump at the same time on a different star. So we were kind of scratching our heads thinking about what it could be. One of our first suspects was the high gain antenna. We knew that that every 10,000 seconds or so, every few hours, the antenna that sends the data down to the Earth has to repoint to different ground stations. And so this was just kind of an unavoidable thing that could happen. It could cause a pointing variation. And one did occur during the observation, and you can see it causes a small change, pointing offset, but it recovers in less than a minute time scale. And so this was something we thought in our minds, maybe that would be something that could cause problems in light curves. And this was our first light curve we saw, but the high gain antenna move didn't happen. It was sort of roughly the same time, but occurred like 20 minutes earlier than the jump that we saw. So this was kind of eliminated as our first suspect. The next thing we were kind of looking at was the images from the weak lens time series, and you just look at them. It's pretty hard to see if there are any changes. But if you take the first image and that as a reference, and then divide the next image by that you get a differential image. So as we go through and look at this difference images, you can see if there are any changes in the point spread function. So this is something I was doing like right as I was getting on a plane and looking at it. And then all of a sudden there was this huge feature and I was like, oh, I know what it is. But there was like time to take off. Everyone stowed their tray tables and with their seats in their upright position. So I was like, I know what it is. I'll tell you when I land. And then we saw this big, strong signature in the weak lens time series. So it was actually kind of unplanned, but happy, useful tool. So when we planned out these observations, we needed something to spread the light out over a lot of pixels. And we did that because we learned from many other space and ground-based observatories that makes you less sensitive to some systematics if you spread over the light over more pixels. And so, before we knew the jitter was going to be, pointing performance was so good, it reduces your sensitivity to jitter and some other systematics, and also spreads the light out. It makes it easier to observe bright targets. So we just chose this as a way to spread the light out, but it also is the same tool that is highly sensitive to the mirror surface. And so you could actually use these weak lenses to do what's called a phase retrieval to figure out what the primary mirror of JWST is doing during this sequence. And so we had Alden Jerling from NASA Goddard do this phase retrieval using the weak lens to figure out what the mirror surface is. And so you can see these, it's an incredibly sensitive method that can figure out nanometer changes on the wavefront error. So you can see a change in the wavefront surface. And what you can see there is a tilt. And that's where one of the hexagonal primary mirror segments changes orientation. And actually, when we looked more closely at this, we found there were two tilt events that happened in this time series. And there was also a jump on our time series corresponding to the second tilt event. And so this is kind of new kind of systematic that we're dealing with JWST. You can see the tilt events in a couple different ways. One of them is to look at the fine guidance sensor data, and this is available with all the modes. You can look at the images and see there's actually a change at the time of the tilt event. So the point spread function changes because the mirrors are now aligned differently. And so that's one way. Another way to sense these events is looking at the full width half maximum of a star. So this was on the bottom, the full width half maximum from our GRISM time series, and this is something you can be done on all the time series modes to check and see if there are any small changes. And it's a pretty subtle change in the full width half maximum, but if you look at high precision, you can sense these small changes during these tilt events. And so here's just different ways, different statistics you can use to sense these events. And if you look closely on them, there are kind of these step function changes. So we were able to look at the few second time scales with the near cam instrument, looking at different samples up the ramp And you can see that they happen in about 1.4 seconds or below for as we go through the sequence. And so these mirrors are actually just moving very rapidly, and it's not any kind of gradual change in these tilt events that we observed. So the mechanism of them is still somewhat unknown. There's the hypothesis is that it's building up, the mirror backplane structure builds up some strain, and as a function of thermal gradients, or as the telescope cooled, and then those are released suddenly. And so this shows a time sequence. This was made by Marshall Perrin and shared recently, of what the wavefront is looking like over time. You can download, this is all publicly available data that they collect on the mirrors, and you can see when these tilt events happen. So there appears of relative stability, and when looking at a time series like ours, 6 hours, we were somewhat unlucky in finding in those two, and that was earlier in the mission when things were still cooling down a bit. But they can happen later in the mission too. And this is just a few weeks ago there were some tilt events, so they haven't gone away completely, although they have decreased somewhat over time. I think there's a question here.
Carl, do you have a clarification question? Go ahead, please.
Yes, hi. Is there a way to tell, or is anybody investigating whether it's the mirror segment itself or the backplane structure that's causing this?
I think that there is some data on the backplane that has, when there's a larger one, I think there's a way to sense it. But I think for the smaller ones, there isn't a lot of telemetry that tells us for sure.
Yeah.
Yeah. So if this is caused by the telescope cooling, then is there like a certain projected time at which the telescope reaches an equilibrium?
Yeah. So I mean, it should have reached equilibrium in May. By the time we were doing the observational sharing with the tilt events in May, it was reached a steady state for a given, if you're staring at a given pointing. There are some small thermal gradients as it moves around the sky, and so maybe those could be happening. I think Marcia maybe will weigh in. She has some good insights.
Yeah, Marshall Perrin has made a plot of telescope wavefront error with time and big excursions. Everett already has it in, so you can see that the number of big excursions has declined quite a bit, and so that suggests that this cryo stress relief argument might be the right one.
All right, thank you.
Yeah, so when earlier in the mission there were sometimes up to a few a day in some cases, and now it seems more like week long, a few weeks sometimes, but they haven't disappeared entirely. So yeah, this shows the wavefront error as a function of time. We can see these jumps from things like tilt events. There's occasionally a micrometeoroid impact as well, but those are less frequent than the tilt events. And a lot of the time, it really isn't any. The performance is so good. This green line shows the 80 nanometer level of wavefront error. They don't even make a correction because the PSFs are just so tight. The performance is so good. But then when there is something that occurs, like a tilt event, they will do a correction. There are these hexapods that can change the shape a little bit and the orientation of the mirrors. Another thing we were looking at was using an optical model from these tilt events to predict what would they do to the time series, to see if this is kind of a predictable correction. And this is still early work. On the short wavelength, we were able to predict the optics predict the size of the jump very well. On the long wavelength, they're under predicting it, and so this is still work in progress, trying to figure out exactly for tilt what it will do to a time series. But fortunately, these, at least most of the tilts we see are these very short things, very short events that are sporadic and can be just fit with a step function for before and after. And that does a pretty good job of removing them from the time series. So next, I'm going to talk about settling timescales. So this is the near cam observations, short and long wavelengths as a function of time. And just to give you a sense of reference from the Hubble Space Telescope, it takes 90 minutes to do its orbit. And usually the first orbit is thrown out. Typically, most analyses of time series, the first 90 minutes of data is thrown out. And what's going on with the Hubble Space Telescope is there are these traps in the detector that are filled as you're observing a bright target, and it kind of follows this ramp and achieves somewhat steady state. With JWST detectors, these timescales are and amplitudes are just much smaller. So on a long wavelength, we really only have upper limits on any settling. It seems like basically from the first integration, or sorry, the second integration, the very first one can be anomalous. So the second integration, it looks extremely stable, and there's no sign of this kind of ramp. On our short wavelength, this near cam A3 detector is the one that has the most charge trapping behavior. There is a detectable time scale. It's on the order of 10-15 minutes to settle, but that's still a pretty small fraction of what we had to deal with the Hubble Space Telescope. And also the time series observations have to build in an hour of kind of scheduling window of slack. So if you kind of forward weight your observations, there's an hour of settling time. This detector charge trapping will settle out pretty well by the time you're really starting the science exposures in your observation. But you can also see there is some long time scale trend. It was seen also in the science observations of WASP 39b. So this is something we're still looking at as to whether, some of these could be astrophysical. Stars are not perfectly steady, but there may be also a long time scale trend that can be fit with some polynomials or a Gaussian process kind of approach for fitting these light curves. So now I'm going to talk a little bit about like the photometric performance and some limitations from 1/f noise. When you do a correction for the jump and the baseline and exponential, the light curve behavior bends down very nicely as a function of time. And so this is good that the noise basically falls as a square root of n measurements in the time domain. And so these bend down very nicely. These are measurements from the near cam instrument, and they're pretty similar across the near infrared instruments that we've measured. Binning in the wavelength direction, so binning pixels together doesn't go down as nicely as a square root of n. So this shows the number of wavelengths you're adding together and how the error drops with the number of pixels, basically. You can see here that it peels up. There's some evidence for excess noise when you get to large bins of wavelength and pixels. And one of the causes of this is 1/f noise. So this is a little aside on how the detectors are read out. And what happens is that you don't get a picture simultaneously. There's a sequence moving through the pixels. So as you go across a row, every 10 microseconds, a new pixel is read. And then the next row is read in this 1 by 1 pixels, and the next row all the way through the image with some overheads on the between the rows. So what you can do is look at this in terms of a time series within a frame. So this is usually where we think about like frames to frames, looking at time series of exoplanets, but this is within inside an image. You can make a sequence of the measurements and the noise and unfold an image into a time series. And so when you do that and take a power spectrum, you get this power law that's approximately falls as 1 over frequency. So there's the most noise at the low frequencies or long time scales. There are correlations, and then at the high frequencies or short time scales, there is less noise power. So this is something we knew from the ground, and it is a limitation when you're trying to combine together pixels. The way I think of it is kind of is similar to when you're driving. If a road has really bad washboard and you're driving on it, then it shakes your engine, and it's pretty bumpy ride when you're trying to drive, because there are a lot of correlations between the bumps on the road. But like a well-maintained gravel road could still be pretty rough, but doesn't cause that same kind of correlation and damage and bumping on your car. And so a similar thing happens with the JWST instruments. You can see this striping behavior along the rows due to this 1 over F noise. And so the noises correlate. When you add together these pixels, they don't fall down like the square root of n statistics, as compared to the independent white noise. Identically independent white noise does fall as the square root of n when you add n pixels together. So one of the methods we've been applying to the near inference instruments is what I call row by row, odd even by amplifier correction. And one of the things it does is just correct the overall amplifier offsets. But then in terms of the 1 over F noise, it subtracts from every row in the image using background pixels, subtracts the estimate of the background. And this, you can see, removes a lot of this banding that happens in the horizontal direction. So this helps a lot with, in terms of 1 over F noise, gets you closer to the photon limited performance, but there's still some power that can't be removed at the short time scales, and then between frequencies that are not measured by the background. And so working on some ways to improve upon this 1 over F correction. But it gets to sometimes have excess noise at the 40 to 100% level, depending on the instrument mode you're looking at and instrument and orientation. So this is somewhat a limitation when adding together pixels on bright sources. So that was kind of covering the performance that we and characteristics of JWST time series that we learned from the commissioning process. Now I'll move on to some of the early release science on the Exoplanet WASP-39b. So WASP-39b was observed by all near-infrared instruments on JWST and as part of the early release science program. And this was 127 authors on this paper. It was really great to be part of such a large collaborative team that works well together, with observers and modelers and model observers all looking at the data independently and together and sharing our ideas and our results to see if we can get the best performance in JWST, and we understand how it works and we can get the same answers. So this shows the light curves of one of the reductions that I looked at with a time series, the near spec instrument on WASP-39b. And you can see these incredibly low noise light curves of the planet across the wavelengths here. And so this is one way to visualize it. Another way is to look closely at put those light curves right on top of each other. And you can see, this is really incredible being able to see this in the light curves themselves. Usually it kind of comes at a later process where you can see the effects of absorption, but you can see the carbon dioxide here actually causes a deeper transit depth. So you can see the separations of colors here in the light curves. And another way to visualize it is in 3D. So I made this animation of the best fit light curves, and you can see from different angles if you line them up. And so here is zooming in on the water vapor absorption on one side of the spectrum, and then where carbon dioxide should be. And you can see that absorption in the best fit light curves without before you even do the fitting of the spectrum. And so before JWST, we had Spitzer, and it had these big photometric bands, 3.6 and 4.5 micron, observing these exoplanets. But there was always a little bit, like we weren't quite sure exactly, you know, there are different things you could fit inside that we think there was carbon dioxide in there, but there are different molecules that could fit in those band passes. And they were also observed at different times. And so there's some lingering doubts we had whether we were really detecting carbon dioxide in the atmospheres of these planets. And then the JWST data comes along and just so clearly and beautifully shows where carbon dioxide is and how much it is in an atmosphere. So you can see the comparison of what we had. And actually something that was comforting is that for the most part, the JWST and Spitzer data agree when you take out these offsets. So this is the spectrum. This is actually only part of the spectrum. More of it is coming soon. The paper is going to be submitted, I think, in any time in the next week. And looking at the full spectrum, that's that to become. But this is just with such a huge, beautiful signature. The team decided to come out with this early paper that just shows the carbon dioxide so clearly detected for the first time in an exoplanet atmosphere. And so this is showing the contributions from different molecules. So you can see that the dominant molecular absorbers here are water vapor and the carbon dioxide. And a nice thing with this big team was observing the spectrum with different codes, different analyses, different assumptions about the planet's orbit and limb darkening coefficients. But overall, these different codes and analyses agreed very well. And kind of to our joy was that the Spitzer measurements were verified pretty well, and we actually were seeing real things with Spitzer. But we just couldn't be entirely sure of them before JWST. So the models worked, the data analysis pipelines agreed very well. Also, the models agreed very well. So these were different grid fits for the best fit spectra for the spectrum that JWST saw, and made different assumptions about the temperature profiles and chemistry of the atmospheres and clouds, but they overall agreed very well on detecting this carbon dioxide feature and similar kind of metallicity or enrichment of metals in the atmosphere. So this plot from Trey et al. 2022 shows our solar system planets and how the composition changes across different elements and different planets. And there's still a lot of, even in the solar system where we can go to these planets, there's still a lot to be learned, and a lot of molecules and here that broken down to elements that we don't have a good measurement for. But there's actually a hope that with JWST and exoplanets, they're at a hotter regime where you don't condense out a lot of these things. So we'll actually measure some of these better in exoplanets than in Saturn, for example. And so the WAS39 measurement, this is still a preliminary. This early paper didn't do a full retrieval to get a posterior distribution of exactly the metallicity ranges, but it gave a best fit between all these models, and they agreed well across models for the planet enrichment in carbon. And so we've been, with Hubble Space Telescope, we're measuring oxygen in atmospheres, but now we're getting a carbon-based measurement of the atmospheric metal enrichment. And we're going to have a better constraint on this when the full retrievals are all finished and discussed and debated, and a conclusion is reached from those. But you can see that the initial metallicity is pretty close to what we have with Saturn in this first look. And so this trend that we see in the most massive planet, Jupiter, in our solar system has this lower metal enrichment, and you move to smaller masses from Saturn, Uranus, Neptune, that there's more enrichment of heavier elements and molecules in the atmosphere. is borne out by this this first measurement, and there's going to be dozens and dozens more measurements with JWST to understand these general processes that happen in making and evolving planets. And so one thing that was just amazing about this data was how well the model predicted the observations. And I was showing one of the versions of these to my colleagues, and they were asking, which one is the model, which one is the data, because it just looks so good. And so it was really amazing to see the models perform so well, but then also there's some places where it doesn't. There's this bump here. It's at a few sigma statistically significant result, but there's going to be more observations to follow that are in the works, looking at this at higher resolution. And so this is something that wasn't in the models, and an opportunity to learn something new. And so I can't say, I don't think I'm allowed, it's still embargoed. We think this extra bump is, but there are 2 papers coming all about this bump and what it could mean for exoplanet atmospheres. And so just a way to give you a preview of what's coming without actually giving you what's coming. This is the simulated data. So basically what I showed you is this small portion of it, and there's going to be the whole spectrum with all the instruments, and there's going to be MIRI coming later in the year as well. So there's a lot of exciting results just coming out from this early release science program before we even count all the amazing dozens of planets that can be observed by various programs. So just to conclude, I showed you some of the highlights from our commissioning and lessons learned about the performance of JWST instruments, and that one thing that can happen on occasion are these tilt events. Settling timescales are very rapid and bode well for getting high quality light curves. One of the limitations that can be for the adding together pixels can be this 1/f noise in the detectors. And we look forward to many future science results with JWST coming forward. So thank you for your attention.
Thank you, Everett. Question here in people from in person? Do you have any question to Everett or to Michelle? Okay, for those in online, Andrew.
Yeah, Everett, thanks a lot for this. Sorry if this is a naive question, but the seems that the settling timescale is an instrument response issue. So why couldn't this not have been determined before in the lab?
It's actually something we did measure in the lab, and we actually got a slightly different measurement. So I think what happens, like every time you can cool down these detectors, you can get like a slightly different behavior. And the important thing was really measuring these on the real instruments and detectors and electronics. And then finally, is the lab, one of the challenges with the labs, we had some measurements of it, but it's hard to get a lamp that is as stable as a star is, because we're looking at these 100 part per million kind of changes, and getting a lamp is actually really challenging to make a light bulb stay that steady. But something is like a massive star, it's not too active, is actually a steadier light source than what we can do in the lab.
Great. Yeah, no, thanks.
Okay, there are 2 questions in the chat. Brittany, do you want to speak up and ask questions?
I don't have a question.
Go ahead, Brittany.
No, I said I don't have a question.
Oh, you don't have a, oh yeah, okay, sorry. So Renu, Renu, you had a question. So would you like to speak, Renu? She's asking about, what is the source of the 1/f noise?
Yeah, so I didn't discuss this. The source is the detector electronics that I think it's still, like, I'm still fuzzy on exactly how it's generated, but it's a process. the detectors are read out by these application-specific integrated circuits, ASICs, and basically the electronics. There are these two different electronic components, those and a field effect transistor that introduce this noise when the pixels are read out in this sequence. And so I'm sorry, I don't know, like the solid state physics, I can't explain further the exact cause, but it's something we have to live with. There are mitigations, different kinds of mitigations for the 1/f noise.
Okay, Carl?
Yeah, hi. Another optics question. Is there any data on how stable the primary secondary mirror alignment is, or is it so stable that no one can see anything happening?
So I think what you're asking for, but maybe I'm not fully understanding the question, is this primary data from like, maybe are you asking, like, we can measure it using the wavefront sensor? We don't have like we don't have as much telemetry to tell us what the wavefront is doing, but these weak lens images, there's the one I showed, and then there's a 4 different -4, +4. It can make a combination of -12 to +12 power defocusing of the instruments to make these measurements and do these phase retrievals of what the mirror surface is. And so they do these every few days. But was that the question that was being asked?
Well, you're showing what the segments are doing. So I'm wondering what the larger telescope structure is doing. You know, if the secondary moves a little bit side to side, you get coma in the images. If you is there focus drift, those kind of things, which are horrible in low Earth orbit, but maybe nothing is happening in L2.
Yeah, I'll just comment that there's been no evidence for the secondary moving. In fact, we even skipped the second multi-instrument, multi-field adjustment because everything was so good there. And as far as I know, all of these, there have been very few changes in the wavefront error maps that would indicate any kind of correlated structure motion. There have been a couple of times. You can see one of these on the slide that Everett's got up now. On the second row from the bottom, 3 in from the left, you can see where one of the wings did a tilt. But by and large, the structure and the secondary appear to be very stable.
Okay, thanks.
Thank you. Okay, any other call for last question? Any other question? Okay, let's say thanks, Everett.
Thank you for your question.
In our study.